Suppose R is an equivalence relation on a set A, S is an equivalence relation on a set B, and A and B are disjoint sets. We want to prove that R union S is an equivalence relation on A union B. Now, if you've already seen the proof that if you have a partial order on A and another partial order on B, and these sets are disjoint, then the union of the partial orders is a partial order on the union of the sets. Well, this proof is going to be quite similar to that, right? Because the only difference between a partial order and an equivalence relation is that, well, they're both reflexive, they're both transitive, but the partial order is antisymmetric, whereas the equivalence relation is symmetric. So only the symmetric part of the proof is really going to be different from that proof. But we'll go ahead and do the whole thing, just to have a record of it. Okay. So what does this look like? Well, we have our two disjoint sets, A over here and B over here. Okay. Oops. Try that one more time. Okay, and we have a relation R on this set, which is basically a bunch of arrows among elements of A, and a relation S on this set. And okay, we're looking at the union of these two sets and also the union of the relations. So basically we're taking all the arrows on both sides and throwing them together into a big relation. We want to make sure the resulting relation we get is, first of all, reflexive, right? Well, why is that? Well, if you take an element X, it has to be in either A or B. If it's in A, then we have X is in R, and certainly in R union S. If X is in B, we have X is in S, and again, it's in R union S, okay? So X is always in R union S for any X in A or in B. Okay, now let's think about why R union S is symmetric. Well, for some symmetric, you want to assume that you have any two things that are related to each other, right? So if we have X and Y that are such that the ordered pair XY is in R union S, well then it's either in R or it could be in S. Okay. Now in the first case, everything's completely contained in A, and because R is symmetric, that means we have YX also in R, and therefore in R union S. Or if it's over here, then we have YX in S, and therefore in R union S. So this union relation is also symmetric. And finally, for transitive, well, we get to assume we have two arrows now, right? X is related to Y, and Y is related to Z. And, well, remember, nothing over here is related to anything over here. And so if things are going to match up, we're basically going to have X to Y, and then X, Y, and Z are all going to have to be in sort of the same rectangle here, okay, for these arrows to match up. And in either case, well, over here, because R is transitive, we get that XZ is in R, and therefore in R union S. Or over here, because S is transitive, we get that XZ is in S, and therefore in R union S. Okay, so if you understood that, then you basically understand the whole proof. But we're going to go back through it in gory detail in terms of the givens and goals tables. And I have the proof over here. I'm not going to talk through that, but you can look at it as I go and pause the video if you like and try and match things up. Okay. So, all right, let's start out here. We have a couple of equivalence relations on different sets which are disjoint, and we want to prove the union is equivalence relation on A union B. So let's take some definitions here. There's our three equivalence relation statements. And A and B disjoint means that their intersection is empty. Okay, so first of all, let's prove that that R union S is actually a subset of the Cartesian product of A union B with itself, right? That's what it means for R union S to even be a relation on A union B. Right? If we're going to show it's an equivalence relation, we probably should begin by showing that it's at least a relation. Okay, so we'll use the fact that R is a relation on A and S is a relation on B, which those are subset statements, so the definition looks like that. And remember, we're talking about elements of relations, so that's why I'm talking about ordered pairs here. Okay. And then here's what we want to prove. Another subset statement. And to prove this, we will let x, y be an arbitrary ordered pair and do direct proof. So we will suppose that xy is in R union S and prove that it's in this Cartesian product. And we'll do universal instantiation here, right? Because we have xy in R and in S. Okay, well, we'll use that in a moment, but okay, just drop the quantifiers for the moment. And then, okay, so like I was saying, we have xy in R or in S, and that breaks us up into a couple cases. And what does this mean? The definition of this is that x is in A union B and y is in A union B, so that'll be our goal in both cases. All right, and then here's where we use these statements. Because xy is in R, modus ponens gives us that xy is in A times A, and that means that x and y are both in A, and therefore they're certainly both in A union B, and that's what we needed for our goal. Okay, and in case 2, you're going to use this conditional up here, which came from S being a relation on B, but it's going to be exactly the same idea. So, okay, so you can read that first part over here. First, we proved that R union S is a subset of that. We have our 2 cases, and we're done. The second thing we're going to show is that R union S is reflexive. Okay, so we're going to use that R and S are reflexive to get that. There's the definition of those 2 things, and here's what we're trying to prove. Okay, so we will do, we'll let C be an arbitrary element of A union B, and then we have to prove that C is related to itself in this new relation, R union S. So we can break up that union, and all I'm doing here is just rewriting, changing the ARA notation to ordered pair notation. Same thing over here. We want to show that CC is in R union S. Okay, and then we have some cases. A lot of unions in this problem, so a lot of disjunctions, and therefore a lot of cases. So we've got that. All right, and we have to prove that CC is in R or it's in S, and it turns out that because A and R match up and B and S match up, we're going to make these choices of what to prove in the 2 cases. Right, so because C is in A, we can do a universal instantiation where A, or little a, is going to be C, and we just get that CC is in R, which is our goal in that case. And quite similarly, in this case, C is in B, so we can do universal instantiation here with little b equal to C, and we get CC is in S. Okay. So the proof of that one is right here. And you'll see that actually in all these proofs, in case 2, I said what my supposition was, and then I just said this proof's analogous to that for case 1, because I didn't want to clutter things up too much, and they really are basically the same with some different letters. Okay, third, we show that R union S is symmetric, and we're going to use that R and S are symmetric. All right, so there's the definitions of being symmetric, and here's what it means for the union to be symmetric. Okay. So let's let C and C prime both be arbitrary elements of A union B. So I'm being a little bit sloppy there and sort of abbreviating that. And then I take this antecedent as my given and consequent my goal. And okay, let's just rewrite that in the other notation for clarity's sake. And same thing over there again. Okay, and being in the union means that, well, it's in one or the other, so we have a couple cases again. And think back to the pictures I drew a little while ago. You'll see we're basically saying the same thing we said there, but just with a bunch of notation instead of a picture, okay, instead of arrows. All right, so for if we know that CC prime is in R, then we know that C is in A and C prime is in A, which I'm sort of sloppily abbreviating that way. And therefore, we're going to want to do a universal instantiation on that statement up there, where A becomes C and A prime becomes C prime, to get that conditional. And then we use the fact that CR C prime is given to, via modus ponens, arrive at C prime RC, which, well, gives us that C prime C is in R, which is enough to prove this statement, right? Now in case 2, pardon me, okay, yeah, so, okay, so that gives us the first one. Now in case 2, in an analogous way, using this other universal statement up here, we're going to be able to prove that C prime C is in S, which is another way of proving that C prime C is an R or C prime C is an S. Okay, so that takes care of it. And let me scroll down a little bit. So that was the proof that R union S is symmetric. Again, the proof for case 2 is analogous to that for case 1. And then finally, we're going to show that R union S is transitive. The end is in sight. So we're going to use the R and S are transitive, which is that. And then here's what we're trying to prove. We will, and we're going to need here that A and B are disjoint. That'll be important. Okay. And so we let C, and C prime, C double prime be arbitrary elements of A union B. Assume that these two things are true and prove the third one. Okay. These guys, if we write out these unions, right, it means that either CC prime is an R or CC prime is an S. Similarly, this becomes these two things. And so now I have a union, and, a disjunction and a disjunction, and if you sort of distribute that out a couple times, you're going to get 4 conjunctions with or signs in between them, right? All right, so that's your 4 cases right there. Wonderful. First of all, okay, split that up into 2 possibilities as well. And here's our 4 cases. And bring our other givens down. Okay. In the first case, we are going, why am I allowed to do that? Well, because C prime is an R, we know R is a relation on A, so that tells me that C and C prime are both in A. Similarly, I can tell that C double prime is in A right here, so I can do universal instantiation, and I can do this in the case where A is C, A prime is C prime, and A double prime is C double prime. To get this conditional, and then that combines very nicely with what I know in that case to give me my goal, right? So this is all happening within R. Okay. Now in case 2, here I have sort of one arrow on the from R, one arrow from S, so sort of one in the set A, one in the set B, and well, that can't happen, right? And they connect up at the C prime, and that can't happen because C prime can't be in both A and B. Okay, so we could deduce from that C and C prime are in A, C prime, C double prime are in B. In particular, C prime is in both, and well, okay. So one way of getting a contradiction here is to say, okay, we said that A intersect B is the empty set, so I've just shown that C prime is an element of the empty set, which is certainly a contradiction. Okay, so that case can't happen. Case 3, we again have one arrow on in the set B, one arrow in the set A, so we would again get that C prime's in both, which is a contradiction. And in case 4, everything's happening in the relation S, or in the set B. And so that proof would be very similar to case 1, but you're going to use this other universal statement here. Okay, you're going to be using that S is transitive for that. So that takes care of it. We found out that the middle 2 cases just don't happen, and the first and fourth cases we can take care of. So here's the proof of that one written out, and we at long last are done with part A. Parts B and C will be in another video.